Tension, force-differentiated structural steel design. This presentation is brought to you by the Association of Collegiate Schools of Architecture. My name is Terry Meyer-Boak. I teach architecture at the University of Waterloo, and my passion is steel. The incredible and unparalleled design potential of steel lies in its ability to perform in tension. No other common building material has this capability. Although tensile steel found its initial use in bridge design, it is now being used in a wide variety of architectural applications. If we can understand and differentiate to identify the members that are only ever subjected to tension and those that experience compression, we can use this knowledge to create force-differentiated structures. The design of the steel system on the Grand Arch made clear use of more substantial members to resist compressive forces and thinner cables to resist tensile forces. The design for Porto International Airport continues in this established tradition of force differentiation to create a highly energetic arch system that spans across the departure hall. So in the instance of the design for the Porto Airport, this has allowed for the use of much thinner rods to stabilize the structure. It is pretty clear here that the curved bottom chord of the truss is a compressive member by its size, and that the horizontal ties are in tension. The tubular web members of the truss are acting in compression, but can be smaller due to the decreased compressive loading. The most normal way to connect tension rods to plates is through the use of a clevis. These make simple rotating pin connections. The bottom chord of the innovative trusses in the Pudong Airport use rods, as these elements are always acting in tension. The attachment between the rod and the hollow structural steel compression member is achieved with this innovative steel ball connection. If multiple tension elements are connected via clevises, the geometry must be planned carefully to ensure that the plate to which they are attaching has enough steel and adequate distance between the holes that are drilled to accept the pin connections. As can be seen in the design of this bridge, the fan-like geometry of the tension members has resulted in a varied spacing of the supports to the bridge deck. Had their spacing been required to be even, this would have changed the design of the plate at the top of the mast. Inside the curved glass dome of the Reichstag, a spiral ramp fabricated from custom sections of plate steel is hung from the ribs that form the dome. The spiral walkway inside the Reichstag dome uses a tension suspension system. The ends of the rods use clevis attachments. A custom clevis has been designed to neatly accept two incoming rods to simplify this connection. A tension system is used here to assist in making the span, absorbing some of the gravity forces from the bridge-like connection between these buildings. The plates that connect the tension members to the primary structure are custom formed to accommodate two rods. A turnbuckle is evident. These are used to align and tighten the system as it is being erected. The connector at the lower extreme of the tension member keeps a similar aesthetic, but only needs to resolve a single member in this case. This pedestrian highway overpass uses a tension system to suspend the walkway from steel arches. This is a view to the underside of the bridge, showing the unusual support system for the walkway that has been created with inverted T-shaped steel sections that have been welded to a central round HSS spine. The ends of the inverted T sections include a custom hanger attachment to allow these sections to be supported by the curved box sections of the large arch supports. The architectural use of express tensile cross-bracing was well established in the design of the Pompidou Center by Piano and Rogers. The creation of the connection detail at the center of the transfer of forces has generated some interesting solutions. Here, the rods are accepted by a section of round HSS with a simple cover plate to hide the bolts in behind. Steel is often used to brace timber structures, as in the case of this exterior walkway. This project takes a different approach to the design of this connector, altering the reading of the architecture on this exposed exterior bracing system. Galvanized steel has also been used for corrosion protection. This very lightweight facade of the Munich International Airport required cross-bracing to provide rigidity. The cross-bracing triangulates the structure, with only one diagonal acting in tension at a time, as a function of the lateral loading on the building. The designers decided to use pairs of tension connectors to achieve the cross-bracing as part of this design. If you look to the upper left-hand rod, you can see a very slender turnbuckle. These systems must be installed loose and tightened in place using the turnbuckle. The large custom trusses at the Burj Al Arab use cross-bracing as part of the system design. The design of the plates to transfer the loads across the center of the cross-bracing have been designed to be very slender to make them less apparent in the design. The Munich Olympic Stadium is an early example of the use of a mast and suspension system. There is a very obvious contrast in the nature of the compressive mast structure with that of the large cable suspension system that gives form to this glazed roof. The system clearly differentiates the loading on the members, assigning much more substance to those in compression and using lighter cables or rods for those in tension. Custom connectors were fabricated to serve as the clevis attachments, as these were not yet in regular production at that time. The Munich airport also makes use of a tensile system to brace the masts and support the glass and fabric roof of this convention structure. From a design perspective, the light steel members match the light nature of the fabric roof and its form. It is easy to see that the triangular tubular masts are acting in compression and the cables acting in tension by virtue of the sizes of the members. Where the glass and fabric roof meets the mast, the different steel systems are differentiated by color. The gray of the support system for the roof glazing, allowing the white of the mast structure to visually dominate. The light cross-bracing system for the glazing is almost imperceptible when viewed from the ground, yet essential for stability. The glass and fabric roof of the Sony Center is supported by a cable and mast system. The mast is made of heavier steel sections and is acting in compression. The system in this case is suspended in midair and is braced back to the circular truss at the upper edge of the surrounding buildings. The resolution of the connection of the numerous tension members to the base of the mast is quite innovative. The plates are spaced apart to permit welding to the center of the post. The plates are angled to narrow to match the size of the clevis. As there would not be enough steel at the point of attachment of the clevis, the plates are thickened to provide the necessary steel to resist the pull-through forces. This highly unusual bridge in Brisbane, Australia, is created from a tensegrity type structure. Here, the contrast between the member sizes of the compression masts and tensile members is taken to an extreme contrast. The roof of the covered walkway is also suspended from the mast and cable system. The angles make this a dynamic space to walk through. The detail at the top of the mast is designed to accommodate the attachment of the clevises. You can see that the plates are differently sized to respond to the loading. Also, the plates have been thickened precisely where the clevis overlaps to provide the additional steel that is required to resist pull-through forces. This detail at the base of the connections reveals the large scale of the clevis attachments and the thickening of the plates again to resist forces. Tension systems have become very popular for their ability to create expansive coverings of a lightweight and sculptural nature that take advantage of their structural properties. Exploiting force-differentiated steel structures holds much promise for design innovation. I've only touched upon some of the basic ideas behind the exploitation of tension in steel design. For more information and lots of case study examples and photographs to inspire your work, feel free to connect with me on my AESS Facebook page. And for more detailed information on designing with architecturally exposed structural steel, check out these books on the topic. They are filled with plenty of photos like the ones included in this presentation and more valuable tips on fabrication, erection, design, and detailing.